Now next topic, that is magnetic field on the axis of a circular current loop. Suppose as shown in the figure, we have a circular current loop having radius equal to r. Which one is carrying current I as shown in the figure. Now this loop, or we can say the ring, that is placed in the vertical direction, or we can say in the vertical plane, in such a way that the axis of the ring, that is coinciding with x-axis. And we want to find the magnetic field due to this current carrying loop at any point on the axis of that loop. Suppose here we consider the point P, which one is at a distance x from the center of the loop, and there we want to find the magnetic field. Clear? Now here we have to use Biot-Savart law. In Biot-Savart law, we already discussed this thing, how one can find the magnetic field at a point due to any current element. So here we have to consider infinitesimal small current element on the circumference of the ring. And if we calculate the magnetic field at point P due to that particular current element, then after, if we consider the entire ring divided into this type of so many infinitesimal small current elements, and for each one, if we take the magnetic field at point P, and then after, if we take the summation of all those, then we will get the resultant magnetic field. So let's first take only one current element, and that is this current element IDL. Okay. And due to this one, let's calculate the magnetic field at point P. Suppose point P, that is at a distance r from the current element. Now, here as per Biot-Savart law, the magnetic field at point P due to this current element, that will be perpendicular to both IDL and R. So here IDL, that is in the tangential direction to the ring. R, that is radial one here. So angle between IDL and R, that will be 90 degree. That will be 90 degree. And now perpendicular to both IDL and R, if we place the right-handed screw and if we rotate it from IDL to R, then it will move in upward direction like this. And that is perpendicular to both IDL and R. So at point P, perpendicular to R, we can represent the magnetic field dB as shown in the figure. Clear to all of you? IDL and R, both are perpendicular to each other. To understand it, consider this figure. See, this is the current element, and this is the position vector of point P. So angle between R and this current element that is here, and that is 90 degree, because this is tangential one and this is radial one. Clear? And now for perfect understanding of the directions, I am taking one ring here. Now be careful. See, this one is the ring. Okay. Now its axis, that is somewhere here like this. Clear to all of you? Now current element that is here and current element that is tangential one like this. Clear to all of you? Here the current element that is towards me, and this one is axis. So with respect to this current element, you can represent the position vector in this manner. Got the idea?
Yes, sir.
Now keep this ring in your mind. Here is the current element tangentially towards me. This is the position vector. Now, to represent the direction of dB, I am removing this ring, and now I am taking the current element like this. This one is the current element that is towards me, and this is our position vector. Okay. Now perpendicular to both, if I place the right-handed screw here, clear, in this way, and then after from IDL to R, if I rotate it, so in this way, if I rotate, it will move in upward direction. But to fix the direction, we place the screw here. Actually, we want to find the magnetic field at this point. So now take this particular vector here. So at point P here, our magnetic field that is like this. Clear to all of you? Now here, if we take the angle between the radius of the ring and the position vector of point P, that is theta, then angle made by this field vector dB with respect to x-axis, that will be also theta. So we can take two components of this magnetic field dB, one that is dB cos theta, that will be along the x-axis, another one that is dB sin theta, that will be perpendicular to x-axis. Clear to all of you? Now suppose here we consider another current element exactly diametrically opposite to the first element. This first one is represented with blue color, and exactly diametrically opposite current element is represented here with black color. Now with respect to that, P that will be exactly at distance R from the symmetry of the figure, you can understand. And perpendicular to R, the magnetic field here that we can represent as dB dash. Now here dB and dB dash, magnitude wise both will be same one, and directions are as shown in the figure. Now for dB dash, if we take two components, then again we will get dB dash cos theta along x-axis, but dB dash sin theta, that will be in negative y direction means opposite to dB sine theta, you will get dB dash sine theta. Magnitude wise dB and dB dash are same one. So dB sine theta and dB dash sine theta, both are magnitude wise same but mutually opposite. So this component will be cancelled. It implies that if we consider any current element on the ring, then its contribution in the magnetic field at point P, that will be dB cos theta. Its sine components will be cancelled. Clear to all of you? Now, from the figure, we can write here, as per Pythagoras theorem, this small r square, that is capital R square plus x square, and cos theta, that is adjacent, means capital R, upon hypotenuse, that is small r. Keep this thing in your mind. Now, the magnetic field due to the current element as per Biot-Savart law, that is given by mu 0 upon 4 pi I dl sine alpha upon r square, where alpha, that is the angle between I dl and the position vector of the point. Now see, in this particular figure, I mentioned this thing. Easily you can understand the angle between this current element and this position vector, that is somewhere here, and that is 90 degree. So here alpha, that is 90, means the magnitude of the magnetic field, that we can write mu 0 upon 4 pi I dl upon r square. But we already discussed this thing. Only cosine component will present at that particular point. Sine component of the magnetic field produced will be cancelled out. So magnetic field at a distance x by this particular current element, that is dB cos theta. So we can write mu 0 upon 4 pi I dl upon r square into cos theta. Now mu 0 upon 4 pi I dl r square, that we can replace by capital R square plus x square, and cos theta, that is capital R by small r. So we can rewrite this one as mu 0 upon 4 pi I dl upon r square plus x square as it is. R upon this small r is now replaced by capital R square plus x square raised to 1 by 2. So here in denominator, r square plus x square raised to 1 into r square plus x square raised to 1 by 2 will resultantly give you r square plus x square raised to 3 by 2. So now our equation turns to dB at x, that is equal to mu 0 upon 4 pi IR upon r square plus x square raised to 3 by 2 dl. Clear to all of you up to this one? Now see, if we take the integration of this equation over the circumference of the ring, then we will get the resultant magnetic field produced at point P due to this current carrying ring. So B at x, that is integration of dB at x. And this integration is carried out over the circumference of the ring. Therefore, this symbol is placed here. Now, mu 0 I r upon 4 pi into r square plus x square raised to 3 by 2. That is constant one. So it is taken outside the integration. So we can write integration dl. Now if entire ring is divided into so many infinitesimal small line elements dl, 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 dl. And then after, if we take the summation of all these, then we will get the circumference of the ring. So we can write this integration dl, that is nothing but 2 pi r. So now our equation, that is mu 0 upon 4 pi IR upon r square plus x square raised to 3 by 2. And now this integration dl, that we have to replace by 2 pi r. So pi cancelled. This 2 by 4, that will give you here 2. So resultantly, you can write this r into r, that is r square. So b at x, that is mu 0 I r square upon 2 into r square plus x square raised to 3 by 2. This is the resultant magnetic field produced by the current carrying loop having radius r and carrying current I at a point on its axis which is situated at distance x. And at present, our axis, that is coinciding with x-axis. So in vector form, if you want to write this equation, then simply multiply by I caret. If the axis of the ring is coinciding with y-axis, then you have to multiply this one by j caret. So in short, you can understand this thing. The magnetic field due to that current carrying ring at any point on its axis, that will be along the axis. That will be along the axis. Now, at present, our ring, that is with only one turn. But suppose here n number of turns are given to you in the ring. Then very simple. You have to multiply this equation by n. Means your magnetic field at that point, that becomes n times. Clear to all of you? Now magnetic field at a point on the current carrying ring, axis of the current carrying ring, that is B at x equal to mu 0 I r square upon 2 into r square plus x square raised to 3 by 2. This we derived. Now suppose x is very much greater than r. Means the position of the point on the axis, that is at large distance compared to the radius of the ring. Then we can neglect this r square in the denominator. So our equation turns to mu 0 I r square upon 2. This x square raised to 3 by 2 will give you x cube. In vector form, you can write it by multiplying with unit vector in the direction of the axis. Now, if we want to find the magnetic field at the center of the loop, now at the center, we can write x equal to 0. So, magnetic field at the center. So, in this equation, take x equal to 0. So, you will get mu 0 I r square upon 2r cube. So, magnetic field at the center of the current carrying loop will be mu 0 I upon 2r. And in the vector form, you can write it by multiplying it with unit vector in the direction of its axis. Clear? And if your ring that is with n number of turns, then B will be n times. Very simple thing. And here, say, previously we discussed this thing. If you take any current carrying straight conductor, then if it is carrying a current, then how the magnetic field lines are in the surrounding of it, that you can understand with the help of right hand rule. You have to hold your conductor in right hand in such a way that the thumb that is in the direction of the current. So the fingers as enveloping to your conductor, in that manner the magnetic field produced by it is enveloping to the conductor. Now, in case of ring, suppose we take the fingers in the direction of the current. Here the current is taken in this direction like this. So if you place fingers in the direction of the current, then automatically your thumb will point the direction of the produced magnetic field. Clear to all of you?